few things. Let's say we have a matrix like, for example, 1 minus 1, 3, 2. That's A. Now I want to take the inverse. And there are some things that I would definitely recommend to know first before going into this one, and that is elementary operations, Gaussian elimination, and taking the inverse of a matrix, and also matrix multiplication. So these 4 things I would recommend, because this will be sort of an interest video about how you can describe the inverse of a matrix by multiplying it by an array, a chain of concrete, particular simple matrices in order to get to the inverse of it. I'm just going to run through first quickly through the algorithm to get the inverse of a matrix. So let's see. To get the inverse, I'm going to write this identity matrix on the right and the original matrix on the left, and provide elementary operations until the left side becomes an identity matrix 2 by 2, and the right side, whatever that becomes by that point, will be the inverse to the original matrix. So again, I would recommend to have some prior knowledge of taking the inverse of a 2 by 2 matrix for this one. It will be very useful. So actually there's 3 steps. So this is first step. Second step will be, well, actually we do it already here. So I'll write the second step that will be applied for the third one on the second one. So divide the second row by 5. And the last step would be to add the second row once to the first row. And that gives the final result. Finally, we get inverse on the left side. Second row is unchanged, of course. All right. So these 3 operations got us from the original matrix to the inverse, and from the identity on the right side to the identity on the left side. That was what was necessary. The identity had to become this left side. Elementary operations, regardless of this vertical line that makes the matrix, 2 by 4 augmented, operations apply to the whole row always, as usual with augmented matrices. So this is the inverse. And now let's look at the interesting part about, the goal of this video. And that is to look at concretely how we can re-express it. So what we did here is we took the original matrix and we added the first row minus 3 times to the second. Then we divided the second row by 5. Then we added the second row once to the first. That's it, 3 steps. And I want to express it as a multiplication by some matrices. In this case of the same dimension, we have 2 by 2 matrices multiplying from the left, A, to give the final result as the inverse. So let's see. We can express this. It's called elementary matrices, and these are made from identity to which is applied one operation, namely the same row operation like we did in order to get the step in the original matrix. So we can actually take an identity matrix, apply the same operation like we did here to it, and if we multiply this matrix by the elementary matrix from the left, we'll get the same result like we got with that step in the algorithm. So let's see. The first initial matrix, 3, we can multiply from the left by something so that it gives the next step. So what on the left would it be? Well, We will always start with identity. It's not the identity, by the way. Spoiler alert, it's not the identity. And spoiler alert, it's not the identity because this would just be the same. This wouldn't be right. We now have to apply to the identity the same thing like we applied here. We actually added the first row minus 3 times to the second. So here will be a minus 3. So we slightly changed the identity. And now it became a matrix that if we multiply this one from the left by, we will get the next one. And it works out. I can check it, but let's just believe it's true because actually we can check it quickly. But so it's 1 and 0, yes. Minus 1 and 0, yes. Minus 3 and 3 is 0. And so on. So it's fine, it works. And I will call this one E1. Just the matrix that multiplies the original one to the left side. And of course, matrix multiplication is generally not commutative. So we have to pay attention from which side. So we're doing it from the left side. So E1 is this. We multiply this by E1 from the left to get this. And in the same way, we will think of what matrix can be the one that transforms this into this. I write template again. I write the identity one. And I think I need to change the identity in the same way like we changed it with the 2 to the third step. We divided the second row by 5. That was all that was done in this step. So I do it to the identity as well. And again, it works out. Indeed, if you multiply by this matrix, this thing, so you apply to this matrix from the left, this one, you get this one. So that's great. So our E2, I will call it the second elementary matrix, E2, is this. And now let's think. Now we're at this stage. 1 minus 1, 0, 1. 1 minus 1, 0, 1. What 2 by 2 matrix, again, the same size from the left, I multiply this one by in order to get the final stage. So 1, 1, 0, 0 of this algorithm. Well, this algorithm led us to the identity matrix here, so we're looking for the result here. So basically, it's sort of the inverse of this one, but again, this one is finally easier to take an inverse of. We know it will have to be, because of this context, simply identity to which is applied the same thing like we apply to this one itself. So apply plus 1 second row to first row. So this one becomes 1, and that's it. So E3 is this one. So that's very interesting. Now we got it. And to conclude, how we can think about it is basically just a chain of multiplication by these matrices gets us to the inverse. Because they describe precisely that one elementary operation. That's how they're defined, elementary matrices. And that's very interesting. So what happened is we got A, which was, let's just write it all out explicitly in the end. And to the left, we first multiplied by, let's have more space for it actually. We had A. That was 1, minus 1, 3, 2. And to the left, we first multiplied what we had so far by E1. Then we multiply all of it from the left again by E2 to get this step. And then we multiply all of that by E3. And so that's it. This chain of 3 elementary matrices, and there's associativity, so the parentheses we can freely change. So I can just remove the parentheses between the matrices. And so I can write it a bit like one, or change them as I want for the scheme to see how it works. These are E1, E3, E2, E3. I mean E1, E2, E3. I'm just rewriting the same. So this whole thing, these 3 matrices, if we multiply together, that's what we needed to multiply on the left to the original matrix in order to get the inverse. That's it. Very simple. And in other words, I can just write out their names. So what we did is we took A, we applied E1 to it from the left, then we applied to all of it E2 to the left, E3, and the parentheses order doesn't matter. The associativity is there. So we can say that basically this thing to the left of A created A to the minus 1. Alright? And I can just also write it as this. The order matters because there's not commutativity guarantee, but we have this. And we can freely change this equation according to the rules of matrix multiplication, of course. We can take inverses and kind of transform this equation to different forms to see different facts out of it. Alright? But the main point here, the interesting point to take away from this one is basically if you take row operations, each of those can be described by a slightly changed identity matrix, a simple matrix called elementary. And then if you just multiply the chain of them in the correct order, they represent all, they can basically transform the original matrix into the inverse one. So that whole algorithm of getting the matrix into the inverse one is done by a matrix that can be explicitly stated as the product of these three matrices, which will be a 2 by 2 matrix of the matrix of the same dimension, like all three of them.